Hello, this is the simplex algorithm tutorial. We're going to be working on problem 2. The first question is, before solving the problem, could you expect a large number of simplex iterations? Well, the number of simplex iterations is equivalent to the number of basic feasible solutions for this LP. Since the simplex algorithm moves from one basic feasible solution to an adjacent basic feasible solution until it finds the optimal one. Hence, to put an upper bound on the number of simplex iterations, we try to put an upper bound to the number of basic feasible solutions. So the number of basic feasible solutions is less than or equal to CNM. M is the number of constraints in the LP, excluding the non-negativity constraints, which is here 2. And N is the number of variables in the standard form. This is the standard form of our LP, which is basically the same thing, except that we added slack variables, one slack variable to each of our constraints, and we replaced the less than or equal signs by equal signs. So the number of basic feasible solutions is less than or equal to C52, which is equal to 5 factorial divided by 2 factorial multiplied by 3 factorial, which is equal 10. Hence, we can conclude that the maximum number of iterations is 10. Okay, so now we move to question 2, which is to find the optimal solution using the simplex method. So our first basic feasible solution, BFS 0, is going to be to contain S1 and S2. This is the easiest way to do it. You already talked about this in the lecture. The easiest way to start the simplex algorithm is to set the original variables, which are here x1, x2, and x3 to 0, and start the basis with S1 and S2. To fill in the C row, we just put the coefficients of the slack variables, which are currently in the basis, in the objective value. Of course, in the objective function. Of course, you can't see them in the objective function because their coefficients are zeros. So we have 2 zeros here. To fill in the rest of the cells, we basically have to copy the coefficients in the constraints. So here we have -2, 1, -1, and 1 for the slack variable. We do not have the second slack variable in the first constraint, so put in 0. And for the value, it is equal to the right-hand side of the constraint, which is 1. For the second row, we have 1, 1, 0 for x3, 0 for S1, and 1 for S2. And the value is equal to the right-hand side of the second constraint, so it's 3. For the CVAV row, we are going to put the coefficients in the objective function. So it's 5, 2, -1, and zeros for the slack variable. This value is going to be the value of the objective value when we have S1 and S2 in the basis. Hence, it's going to be 0 multiplied by 1 plus 3 multiplied by 0. So it's sum product of this by this, which is, of course, 0. Okay, now we have tab 0 ready. We're going to try to move from this basic feasible solution 0 to another basic feasible solution. And we do this because we know this BFS is not optimal. So since we do not have either zeros or negative numbers in the C-bar row, we have two positive numbers. So to move from this BFS 0 to another BFS, we need first of all to determine an entering variable and an exiting variable. To choose our entering variable, the variable that is going to enter the row, we look at the C-bar row and we choose the largest value. Here it's 5, so x1 is going to be our entering variable. We choose the one with the largest C-bar row because it's the one, the largest its C-bar value, the largest the contribution to the objective value. So for a variable to enter the basis, one other variable is going to have to leave it. To determine the exiting value, we're going to calculate something called the ratio. So the ratio is basically the value divided by the pivot row. This row is going to be called the pivot row. So for the first value is going to be divided by -2. So we're not going to put anything in here. I'm not going to explain why, but you should know that when we have to divide by a negative number or a 0, we just put nothing into the ratio. For the second row, we have 3 multiplied by 1. So it's 3. It is the only option here to choose from for the exiting variable. But if we had multiple values, we would be choosing the one with the smallest ratio. So S2 is our exiting variable. It's going to leave the basis, so x1 can enter. The intersection between this column that we called the pivot column and this one, which is we're going to call the pivot row, is the pivot value, which is 1. Okay, now to move from tab 0 to tab 1, we're gonna have to go through 3 phases. Well, first of all, we'll fill in the basis and our CV column. So our basis is going to have S1 and our new entering variable, which is x1, and the CB is their coefficients in the objective function. So 0 for S1 and 5 for x1. Okay, so we said that we have a 3-step procedure. The first step is to fill in the row for our entering variable. This one, we're gonna be dividing the row in the previous tableau divided by the pivot. So 1. It's going to be divided by 1, so it's going to be the exact same row. So 1, 1, 0, 0, 1, and 3. The second step is to fill in the columns of basic variables. Here the basic variables are, of course, S1 and X1. we start with x1. We have 1 here, so it's going to have zeros in the other cells. For S1, it's going to have 1 in the first cell, since it has the coefficient of 1 in the first constraint, and it's going to have 0 in the other cell. So those were steps 1 and 2. Now for the rest of the steps, we're going to have to use something called the rectangle method. For example, to fill in this value, we're going to consider this rectangle. Okay, so the new value of x2 is equal to the old value minus the value in the pivot column multiplied by the value under the old value, and we're going to multiply to divide by this value. Same thing for x3. I'm going to repeat the same thing so you could see it better. So this is the rectangle. I'm going to use a different color. So it's the old value minus the value in the pivot column multiplied by the value under the old value, divided by the value in the pivot column, which is equivalent to the value under the original value. So divided by 1. We do the same thing for S2 and the value. And now for the C-bar row, we're just going to use the same method. I'm going to show you how to calculate this one, the new value of x2 in the C-bar row. It's equal to the old value multiplied by minus this value in the pivot row, multiplied by the value on top of the old value, and we'll multiply by this value. So this is our rectangle. We do the same thing for x3 and s2. So we're now going to calculate to the value of z. As we did last time, it's 0 multiplied by 7 plus 5 multiplied by 3, which is 15. Okay, now we check if this basis is optimal. As you can see, we now have either zeros or negative values. Hence, we can conclude that this basis is in fact optimal. So our optimal solution is x1 equal to x1 is equal to 3, x2 equal to 0, x3 also equal to 0, and s1 equal to 7, s2 equal to 0, since it's not in the basis. Okay, so this is the optimal solution. I will talk about the last question, which is binding constraints, in another video. So thank you for listening, and let me know if anything is not clear.